Okay, we are recording to the cloud, so James could grab it later too. All right, Manfred, the floor is yours.
Okay, I see. Am I sharing? Can you see this?
Yeah, we can share your, we can see your shared screen.
The whole screen or just the
Um,
presentation?
The whole screen.
Oh,
yeah,
I
it's the
see.
whole
Okay, I
screen.
didn't do this right. Sorry about that. Let me see here. Okay.
No, we could see
Yeah.
just the spreadsheet. We couldn't see the
Yeah, that wasn't
presentation.
right. Okay. This one here should be shared. Okay, that I think is better, huh?
Yeah,
That's PowerPoint, yeah.
Let me make it a little bit larger here. So fiddling here with different. Okay, I see. That do you see the full page basically?
That's good, yeah.
yep.
Excellent. Okay, thank you. All right, so I built this loop antenna from a bicycle rim actually, and I was asked to share my experiences here. And to preface this, I want to say that I'm certainly not an expert on any of this, and I'm sure there are other people in the club here, even online, probably have a lot more experience. So just bear with me and let me know, of course, if there's anything. If you have a question or comment or a correction or whatever. So okay, so I made a little outline, and also to bring us on the same page, I figured it would be useful to have a few slides on loop antennas in general for those who are not entirely familiar with those, and then I'll show you what the construction is that I did, a little bit on performance and modeling as to what to expect, and also RF safety. You have to be careful with those antennas and future work, and then there's a whole slew of useful references at the end. Right, so regarding a small loop antenna, so a small loop antenna is basically a loop, as it says, with a typical circumference of 1/10 of a wavelength or less. So that means for the 20-meter band, we're talking about 2-meter circumference, and that is distinctly different from a full wavelength loop like a one-element quad. So you can see the little graphics on the lower right here. On the right side, there's an octagonal small loop antenna with a diameter of, or circumference, I should say, of about 2 meters, say, for 20 meters, and it has a radiation pattern, interestingly, that looks like a wheel from a roller blade. And it has gain maxima in the plane of the loop, interestingly, and a substantial hole perpendicular to it, as opposed to a full wavelength loop like a quad, one-element cubical quad, so as to speak, which is on the left, that has the gain maximum perpendicular to the plane of the loop, and somewhat less pronounced null in the plane of the loop. Interesting is also to note that a cubical quad, say, like this, is horizontally polarized, assuming that the feed point is at the bottom, versus a small loop, which is vertically polarized for the same type of feed point orientation. So what is also interesting to note is that the high Q of this resonant loop can compensate for its small dimensions in some sense, and gains back some of the otherwise expected losses. And another interesting thing is also that the electrical currents along the loop, on the small loop, are pretty constant along its perimeter, as opposed to a cubical quad, where you have typically two current maxima, one near the feed point and one exactly on the other side. So that these small loops are usually used for receiving, but you can certainly also make it transmit. But a transmitting loop usually requires some modifications and enhancements, shall we say. It needs to be a little bit bigger, typically between 0.1 and 0.3 wavelength circumference, and it needs to be able to handle very large voltages and currents. So that is something we need to keep in mind. All right. So then what about advantages and disadvantages of a small loop compared with the other types of antennas? It's physically small. Certainly HF versions are very, very small compared with their full-size counterparts. And it's useful to be used for constrained spaces or for portable operation, which is the case in my QTH. I don't have space, unfortunately, to put up a large antenna outside. So that is, and I like mobile and portable operations anyway. So that's where my inclination came from to try this out. Another advantage is it doesn't require ground plane or counterpoise, and it has a pretty narrow bandwidth, which reduces, as I already said, noise and other interference sources. And it's really relatively easy and low cost to build, at least if you start with a modest version. The catch disadvantage is it has a very narrow bandwidth, so it does require frequent retuning, as we'll see. But if you go to use it for, say, digital modes, FT8, that may not be a problem. All right. So here's an interesting statement. What can be expected from a small loop? VK5KLT said this in an article which is quoted, referenced below it on the last page. So he says, a properly designed, constructed, and sited small loop of nominal 1 meter diameter will equal and oftentimes outperform any antenna type except a tri-band beam on the 10, 15, 20 meter bands, and will at worst be within an S point or so of an optimized monoband 3-element beam that's mounted at an appropriate height and wavelength above ground. So that is an amazing statement, actually, and it actually in some ways sounds too good to be true, but it must be given a closer look. So one cannot just obviously let that sit and not get excited about it. So here's what I did then to get started. I should say I did not try to build an optimized loop as the first attempt. I did try to build something quickly, inexpensively, just to see what one can achieve, how it works, how to tune it, how sensitive is it, and so forth. And I came across pictures in researching this on the internet. I came across pictures and some descriptions of other hams who use the bicycle rims as the main radiator of the loop. So what did I do? I went to the Bike Works Seattle shop, used bicycle shop here near, which is only 1 block away here in Columbia City, and asked them if they had used aluminum rim, the largest they had, and they sold it to me for $5 actually. So I took that home and cut it open at the bottom and put a piece of plastic in and basically attached it to a 1-inch outer diameter electrical duct, plastic duct. And then went about making the feeding loop. You can see that here to the upper left, the feeding loop is one way to excite the main loop, and it is usually about 20% in diameter of the main loop. So in this case here, the main loop is 24 inches. So a feeding loop of about 5 by 5 inches would be about 20%. And so there are some ideas to squish it so that the current flows somewhat more parallel to the outer rim. And I did that. I'm not sure it makes a big difference, but interestingly, it is just attached there with some cable ties and a little bit of Velcro in between to have them not touch. And then the feed point is just a BNC bulkhead that is soldered on here, and so it's just a very simple way of exciting this loop. the capacitor, I also didn't pay much attention to getting a good one. I just wanted to get something quickly, and so I ordered this online from Amplified Parts. That capacitor is tunable from 15 to 365 picofarads, and attached a dial knob, vernier control knob from Fillmore, and to make sure that that is somewhat firm, so you can really tune it and it's not too finicky. I found in my garage a Teflon spool, so I took the Teflon tape itself, spooled it on some other round body, a large screw or something, and then used that spool to basically attach the vernier knob. So that's what it looks like. Very simple. It didn't take long really to put this all together. And on the right side, you can see the finalized assembly on a photo tripod. It's just couple 6 feet high or so total. That's what I did. Okay. So then, performance-wise, if you tune it, as I said, there's a relatively sharp resonance curve to be expected. On the left side, you can see it's measured with a antenna analyzer at 40 meters, 7.074 megahertz. And on the right side, there's the equivalent measurement made with the spectrum analyzer and a tracking generator. And so it shows the return loss. And that is a little bit easier to use on the right side to determine the 3 dB bandwidth. So you go up from minus 16 dB return loss, which corresponds to about an SWR of 1.35. And you go 3 dB up, and then you see that the width is about somewhat less than 10 kilohertz, actually 8.7 kilohertz in this case. So it does require some patience to tune, and also some skills. And you have to overshoot and it goes back the moment you take your hands off the vernier and so forth, but you can do it. It can be done. Right. So then what did I do to test it actually? I'm doing this all from my office slash ham radio shack here which is located on the 3rd floor of a typical townhouse, wooden building construction. So it's indoors, and it's that's certainly not an ideal situation, and you have to be careful with transmitting, obviously. But suppose I did some tests, and so just tuning it to 20 meters on FT8. And the beautiful thing here is that people are uploading their received reports essentially to a server on the internet on pskreporter.info, for those who are not familiar with how that all works. And then you can go to the website, you put in your call, and so those are all the reports, basically call signs that I heard with that setup here in receive mode over a period of about 6 hours or so earlier this week. And you can see there are reception reports from Europe, a whole bunch from Europe, and certainly a ton from the US, some from the Caribbean, and even one from Brazil and up to Alaska. So that's all quite interesting. On the lower left side, you can see there's an FT8 report, the one from Brazil at minus 14 dB. So that is certainly plenty to have a successful QSO with a station like that, at least from the receive side. Right, so I'm using a KX3 and a signal link audio interface in the WSJT-X software to do those tests. And I should say, of course, as everybody knows, the ionospheric conditions are pretty lousy at the moment, no sunspots and relatively low solar flux. So it's amazing that it works as well as it does. So then transmitting, you can also then see the reports that others have, even if you don't get an answer to your CQ call. You just call CQ for a few minutes, let it run, and then if nobody answers, that is just fine, because the other stations also are uploading your signals to that same server. And you can see there were some signals 4 minutes ago after that transmission at minus 12 dB from somewhere in the eastern US. So that is certainly also plenty to have a successful QSO, and that is with a 10-watt transmit power with this particular antenna on 20 meters from the third floor here indoors, which is also amazing. It doesn't reach all the way to Asia or Europe, but that's fine. That can be done later in different experiments. Here's a case for 30 meters. A similar idea. Now you can see there are all kinds of stations from Japan and Taiwan, China, and so forth, even Australia, that could be heard with that same antenna. Here's a transmission test. Again, the signals were easily heard across the US, and with pretty decent signals at in some Southern California works pretty well, the East Coast, and of course the neighbors here locally. Here the signals also very nicely. And here's an example of how it works on 40 meters. So again, that works pretty well at nighttime to go all the way to Japan and Indonesia and so forth. So that's what I got. So that all looks encouraging. Regarding modeling, so having seen those results, you can of course ask, well, what is supposed to be expected? And there's a spreadsheet that Steve Yates, Alpha 5 Tango Bravo, has put together. You can find it on his website. Just as a simple Excel spreadsheet, and you can just download it and plug in some numbers. And with those loop antennas, there are not many buttons, knobs to tweak. So you can just enter your 5 different input parameters in the green here, like your frequency, 14.1 megahertz. In this case, 2 feet diameter, conductor diameter. Well, this is modeled for a tube, so 0.8 inches is an approximation for this rectangular U-shaped profile of the bicycle rim. And then the important thing is to add some loss resistance and some power level you want to use. One of the important features of those small loop antennas is that they have an enormously low radiation resistance. You can see that further down, the fourth line down in the pink section, only 13 milliohms. So if your radiation resistance is that low, you really want to be sure that your additional loss resistance anywhere in the loop itself, or in the capacitor, or in any leads or connections, is not larger than the radiation resistance. That is the key to knock that down. And this is certainly not ideal with what I did in this bicycle loop. So if your loss resistance is rising, then the bandwidth is also rising, gets larger, and your efficiency goes down. So here you can see in this particular case, for 14.1 megahertz on the right plot, it shows the gain efficiency actually on this red trace, and so you can see that it's minus 10 dB compared with what an optimally performing loop would be. So you're 10 dB down with this setup at 14 megahertz, and at 7 megahertz you can see it is even more like at minus 20 or so. So that leaves an efficiency in the lower single percent range only at 40 meters with that size loop. But if we're putting in a 4-foot loop, then the red line goes way up suddenly, and especially if you also pay attention to reducing your loss resistance, then the efficiency goes up even further. So those are the two primary parameters to worry about. Another thing is, of course, the voltage. Even if you put in 10 watts of power, you can see the capacitor voltage is already 743 volts here. The second row from the right in the pink section, 743 volts. And that goes up even higher if you make your Q higher by reducing, say, the loss resistance. So those are some design features you really have to pay attention about. RF safety warning. The upper left little blurb here is taken from QST, from an article in QST. So I do have a little radiation monitor, a little device from GQ GQ Electronics here in Seattle, and so I tried to to see what I'm exposing myself to by having this antenna, even with 10 watts only, say 2 or 5 feet away. And you can see at 5 feet, which is at the operating conditions set up right on the desk here, you can see the radiation RF flux density is about 700 nanowatt per square centimeters, which is in the yellow range if you look to the little chart that came with it. The magnetic field is 3.1 milligauss, so there you are certainly in the yellow, and the 17 volts per meter electric field is also in the yellow, right? So so it says in this guide, check regularly, be careful. But then if you put the radiation sensor somewhat closer to the antenna, within 2 feet, it's definitely in the lower range where it says avoid long time stay in that area. So you definitely want to be careful not to be close to the antenna. It's putting out substantial fields. Okay. Right. So then the future. So this is what I did sort of to get some experience. And my next loop that is under construction already. I haven't gotten it very far, but I did get the capacitor already, which is shown in that picture. That is a nice butterfly type capacitor with if you take the red short off and the wiper is not needed then anymore. So with that you get a capacity range between 40 and 240 picofarads, and it would be rated up to 5400 volts. So that should be enough to operate at 100 watts. And I want to build that new loop out of a 3/4 inch copper pipe as an octagonal loop, and use 45-degree copper fittings to solder it together, basically. So that should cover 20 meter, 30 meter, and 40 meters with 75, 47, and 20% efficiency, respectively. And that would be a gain of at least 10 dB over the loop that I made so far. So, and then another project for the future would be a cool antenna tuner, auto tuner, such as the one that was designed by TF3LJ. It reads for instance, from KX3 or other radios, the tuning, frequency tuning through a serial interface, and then uses a stepper motor to move the capacitor accordingly. So it just would follow along as you tune your frequency. So that's what I'm trying to do in the future here as time permits. Right.
Manfred,
Yes.
I'll give a question for you, or actually a comment. Can you go back to the last slide?
Yes.
You have to be very careful with these butterfly capacitors because they will introduce a significant amount of losses because the plates are not bounded or bonded, because they're only pressure tied together. This is one thing that they've discovered. You actually go through and figure out how to weld them together, because this will introduce a significant amount of loss. So you really don't buy much with it, but it does work still, because I have just a plain single vein and a wiper type capacitor, but it still works. It still works. You've actually proven everything that I've been saying all along too.
Okay.
All right, carry on.
Great, thank you. Yeah, that's an excellent point. And I have seen pictures online of people who have welded, across those all those stacked sections here between the little cylinders and the plates. I also have seen articles of where people built their own butterfly capacitor out of copper material, which then can be soldered together more easily than aluminum. So to do that, you either have to buy it somewhere, a better one, or find somebody who knows how to solder aluminum and do this properly. So that could be the next version up. And then as you know, there are of course also vacuum type capacitors, which are even better, but also a lot more expensive. So yeah, so there's definitely room for growth. And thank you for your comments. That is very, very good to point out. Right, and so here's a, yes?
Also, at 100 watts, you have a lot more RF safety issues here with running this in the same area that you're able to do your 10 watts. It's really good to see that you did not decide to go any higher in frequency than 20 meters. When you get to 15 and above in these configurations, you're never within the RF safety limits.
Yeah, thank you for pointing that out, Scott. Right, so with 100 watts, I certainly wouldn't do that inside the building here. That would be a nice thing to try out on CW Beach or Field Day side or something like that at RF Camp, but certainly not inside the building here nearby. Right, so this last picture here shows a collection of a small transmitting loops. Some of them are not so small. There's apparently an Italian ham community that is into building loops, and you can see on the left side a huge one for 160 and to 40 meters actually. So that is what that would look like, and I'm sure they can create pretty sizable signals with that. And in the middle is a higher frequency version from 40 to 10 meters, and then on the lower left side is a beautiful setup by K8 NDS, who came up with this nice drive for one of those vacuum capacitors, you know, that are really high quality and have excellent loss performance. So that would be considered a high-end version of loop to put this in there. And then the other three pictures are, which is where I got my idea from. Basically, I can't claim I'm the original inventor of this design. So here you can see those are pictures from England, J4HSK, and the HB9 MTN with the feeding loop shown in the bottom middle, and then DJ3RW. Here's built a loop that is consisting of two bicycle rims of different sizes interleaved, and that way you get to lower frequencies. So that's one way to move the frequency range to say to get better efficiency at 40 meters, maybe even a little bit at 80. All right, so then the last slide here is a collection of references. So there's of course Wikipedia, which with very brief information, but still useful. And then there's Steve Yates' website, AA5 Tango Bravo. He really has a very impressive collection of links and materials, and he also has that a loop calculator spreadsheet online on the website, and you can easily download that and stick in some numbers here, as I pointed out on the earlier slide, and play with it. It's very, very easy to use and nothing fancy, not anywhere close to neck modeling. So very easy. And then VK5 KLT, that has a wonderful article which is 33 pages long in PDF and has a wealth of information. And WF4 MNT, his article is extremely professional engineering work, including blueprints and engineering class blueprints, you know, everything to build the mechanics and everything of drives. Very worthwhile to look at. And then there are some articles of course in QST and also the ARRL antenna book. So that's what I had. Hope that was informative, and maybe you have any comments or questions.
Okay, so I'm going to go ahead and unmute everybody if you if you have any questions or comments.
Excellent. It's glad to have a second opinion of everything I've been saying.
Yeah, it's really cool, Manfred. Thanks for the great show.
Yeah.
As I posted on chat, is there any way that we can get a downloadable copy of his PowerPoint and the recording of this video?
Yeah, Dave, PSN just posted in the chat that we're going to put that up on the webpage. Yeah.
Who should I
And
send
the video
the
would probably show up over in the YouTube Mike and Key group.
Oh, I forgot we had a channel now.
Yeah. So the main video here will go up on YouTube. And Manfred, if you could send that PowerPoint presentation to info@mikeandkey.org, then we can post it up on the presentations webpage.
Okay, we'll do.
Yeah, thanks for your work. It was really good. Good
Yeah,
presentation.
that was
I'd
an
really like
awesome
to-
presentation, especially for such short notice too.
Yeah.
Yeah, for sure.
Thank you all for inviting me to do that in the first place. Actually, I'm glad to do it.
Okay, very
I
interesting.
just love the bicycle rim.
Yeah.
And you basically just proved that, you know, building a mag loop antenna is not rocket science, which has always been my fear of, has been keeping me from going and moving forward. It's like, I need super tight tolerances, and, you know, I got to calculate down to the millimeter, the diameter and circumference, and get the right capacitor. And it's like, boy, a bicycle wheel and an old radio capacitor, you just slapped it together and made it work. So I feel better now.
I want to try that.
Yes, it should. And
Yeah,
and
just
that
make
was-
sure you use low power.
Right.
Yeah.
Don't zap the capacitor. It's 5 or 10 watts is plenty to try. And I just wanted to also learn and get a feel for how it tunes, what it is. You can study all the literature, but unless you start building something, it's a different story, as we all know. And I just wanted to. I also haven't paid much attention to exact resonances or so. I just built it, got the rim, made the little feeder loop and slapped on the capacitor, and it was perfectly tunable between 40 meters and 10 meters, so that was somewhat shocking, actually.
Well, if there's no other comments, I'm going to go ahead. Well, should we, is David back? I don't see David back in. There he is.
Hey.
We woke him up.
I'm still here.
So I think we're good with the presentation. Do you want to see if we can close it out? We can still keep the chat going all night like you did before if you want.
All night long.
I think we're done. You might want to stop the recording.
Okay, I will stop the recording. Yep, thanks for that.
Thanks, Manfred.